Okay, well, I think we can get started. If we get more people, that would be great. But we can get into the topic. And if you hear my introduction, I'm going to talk about solving some of the EV battery challenges with multiscale X-ray vision. And as I introduced a couple of minutes ago, if you ever wish to have X-ray vision like a superhero, that's what we're going to talk today. We're gonna introduce some of potential solutions where the superhero power X-ray vision comes in, and you can see inside battery cells without cracking them open, solving some of the mysteries and sparkling innovation. So let's go with it. And by now, I'm sure we all hear about the global energy needs and the endless tech solutions that are out there. But let's be real, when we think about saving some of the energy problems, we are thinking, and you probably guess it, we're thinking about batteries. But not just any batteries. We need the superhero version of batteries that last longer, are safer and cheaper. And that's why a lot of people are investing and doing research in improving the energy materials that can be used to assemble batteries and components, battery packs, battery modules that create complex devices that power our lives, not only in vehicles, but also in consumer electronics, for example. So let's go on and charge into this topic. We know that one of the biggest challenges facing electric cars, as we might have here of, is the battery. And they face different challenges in terms of manufacturability, performance, load capacity, durability, and safety concerns. And they pose other challenges in terms of quality inspection and failure analysis, because those batteries need to go through a quality inspection process before we put them out in the market or whoever is building them. ZEISS has dedicated into providing solutions, microscopy solutions, and one of them is X-ray. We know that batteries go from nanometers to centimeters, all range of scales. If we think into the particle defects and the electrodes formations, and it goes all the way from particle size to the package assembly. So it goes into the centimeters and sometimes tens of centimeters of magnitude when you create battery packs. And there are different possibilities that we can use to check them. Of course, I don't advise to open them. We know what happens when we try to open them in an unsafe manner. We can create a fire very easily. So ideally, we want to have a way to inspect the batteries inside without opening them. And that's where X-rays comes in, because it's a non-destructive technique and you can see inside of them. X-ray is not the only solution for non-destructive testing. There are other possibilities. What I go into X-rays is that it has the highest penetration depth. There is electron microscopes. That is also a possibility, but then you would have to cut the battery to be able to see inside. And yes, it has high resolution capabilities, but then you need to target. X-rays are potentially the one that goes across different length scales. As you can see here, it covers a long range of different features that you see inside of battery cells. And I have just put here lithium-ion batteries, but this is applicable for any kind of battery that you can imagine. The principle is the same. We're just looking at X-rays. So that's why I'm going to concentrate in X-rays. That's my expertise, but of course, there are also light microscopes and electron microscopes that could complement the workflow. Once you learn from X-ray that you want to look at a higher resolution in certain areas, then you can do some kind of a ion mill and see into an electron microscope. But if we concentrate into the X-ray, then we can classify X-ray instruments in terms of microscopy and X-ray computer tomography or CT. And I would say more of the X-ray microscopy are dedicated to do material analysis and some of the small cells, cylindrical cells, and maybe some pouch cells. When you get into very large batteries, then we're talking something that can penetrate deeper into the materials because you have a thicker kind of component, and then we would have to use X-ray CT. The difference between them being both X-ray technologies, the penetration power, the X-ray CT generally can crack the kV voltage higher than 160 to 225 or more, and that gives you the ability to go through prismatic cells and battery modules. X-ray microscopy doesn't raise the power so high, so it can keep the resolution at a very high level. So there are trade-offs. You can go to X-ray CT to penetrate through denser materials or thicker samples, but then you lose something in terms of resolution. So if you want to keep the resolution high, then maybe it's X-ray microscopy. And if you want to do through the full chain, the process, then maybe then you use both. You use X-ray microscopy and X-ray CT. So I promise you to look inside of some of the batteries without cutting them open, and you've seen already images, but this is what you can see with a CT. You can see inside of the collecting towers. Sorry, my slides are moving automatically. You can see voids, you can see overhand housing, welding, delamination, or deflecting anode, and some particle inclusions, and so on. So this is very important when you are doing quality inspection or assemble of batteries. The workflow, if we think now in X-ray microscopy, what allows you to see at high resolution is the ability to add a detector that has a scintillator and an optical magnification that is going to magnify the X-rays after they are converted into light to give you the ability to see a 3D reconstruction at high resolution. And when I'm talking high resolution is because you will be able to see, and I'm gonna see if my feature works here. No, doesn't work, but you will be able to see some high density particles that are very small and cracks into a cylindrical cell. And this is potentially something that you won't see if you try to use just a single flat panel detector in a micro CT. So this is why it's important to use optical magnification with the 3D X-ray microscopes. And yes, for sure, you can look at particles, but there are other types of features that you would see, like cracks that are generated inside of the batteries after several cycles of charging and discharging. This can tell you how the battery is degrading over time. This is very typical to do studies over several cycles of charging and discharging. The workflow, if I were to simplify a little bit, and let me go back to the previous slide, it would show you, you can get a low resolution scan of the full battery and then zoom in with lenses into different sections of the battery to get the highest resolution down to 2 micron voxel size or below if you want. And the beauty of this type of technology is that not only you see high density materials, but you can also see low density materials as you see there. This is an example of seeing inside of a battery that goes into an electronic component, in this case a cell phone, and you can see over the different layers of the battery or a section of the battery without having to cut it crack open. Just with X-rays, after you do the reconstruction, you can see what is happening in terms of delamination or aging studies of the battery after several cycles of charging and discharging. And this is the workflow. Again, you generally take a full field of view scan of the full battery, and then you go into zoom in to see inside of the battery. Not only do you see the different electrodes, but you see the particle level. Something that sometimes when you use high energy CT or computer tomography systems is very hard to see. So this is the main advantage that you will see with the X-ray microscopes in this case. And you can see some of the delamination. And this is something I was talking about a minute ago. You can do different types of studies, from aging studies, from taking an image of a fresh battery. In this case, you have an silicon anode here that was fully consumed after 200 cycles. And what happened is at about 100 cycles, these particles start to be cracked and being consumed. And after 200 cycles, you don't see them anymore. And this is very insightful. Once you get this information in 3D without cutting the battery, is really great to have it. The aging studies not only will tell you about anode changes, but also the morphological changes on the overhangs or the anode ends of the battery, which are very important because we know if they touch together, then are detrimental for the charging for the battery and can even be dangerous at that stage. And I'm putting reference everywhere for you, so you can check at this later when you look at the recording or if you're taking images. Another thing that is quite important is to try to do fast inspection. And we know the cycles of production of batteries are very fast. So if we want to try to match or at least do bigger sampling of the battery batch, we need to do faster. And what we've done at ZEISS is to implement some types of technologies that go into a fast scan, and not only use a more faster way to scan without using the step mode, but we are including some artificial intelligence algorithms. In this case, if you look at this image, it was reconstructed with Deep Recon, which is an algorithm that we created at ZEISS. And let me explain a little bit of that. It's just basically you use a deep learning network model between the 2D projection stack, which is the battery is rotating. You collect X-rays from different angles, and then you make a 3D reconstruction. When you use the classical way of reconstruction, the classical algorithms, which are analytical, then you suffer from noise in the reconstruction. And the only way to kind of solve that partially is to take a lot of projections, more than 2,000 projections or so, but that implies time. A way to go around is to train a network to identify what is noise when you start decreasing the projections from actual data and get rid of the noise. So you enhance the data, and then you can go backwards and start cutting the projections to below 2,000 to the hundreds, maybe 500 or 300 projections, and see if the data is really good quality. And we've done comparisons, and this is the way to speed the scan. This is a very high resolution scan of a 21700 battery with over 3,000 projections. Very long scan. If you start trying to cut corners with the traditional way of reconstructing, then the problem is you start seeing this type of defects or artifacts. They are not real. They are created by the fact that you use an analytical algorithm and you cut the projections. So it's very hard to cut corners with standard reconstruction. When you use Deep Recon, because you have a model that can identify what is noise from actual data, then you can recover the data with less projections and then in faster throughput scan time because you're collecting less projections. If you were to use all the way to do a very long scan and you don't care about the number of projections, you still can get improvement from a noisy data to a very clean data that gets rid of the noise and allows you to put some segmentation software that gives you an idea of the port network and even identify some of the features in here which are low density to do your simulations if you want to do some type of simulation. And if you want to really take a very long scan, your data is even more beautiful as compared to the traditional way of reconstructing. So if time is not a constraint, and you're just doing purely research, then you can do this and get benefit also from the deep learning algorithms. So that's as far as it goes with the deep learning for now. And this is great. I'm gonna take your questions once I finish. I'm going to switch a little bit now. What happened when you finish a battery and you want to recycle? And there are methods to characterize something that we call the black mass, and this black mass is what is left from the battery after being used. And we can also use X-rays. But the idea is that the end of life, after you charge and use the battery, then you do the battery separation classification, and then you get this type of product that is called a black mass. And then you can try to reuse that, but to be able to reuse that, you want to understand what is inside of that black mass. An X-ray is a really nice instrument or technology that allows you to characterize that. How? Well, if you use X-ray microscopy, you can classify the different particles. You can also use deep learning algorithms, which we have a new flavor here, which is called Deep Scout. And you can verify this with a software that is typically used in SEMs, which is a mineralogic 3D. If you were to use an SEM, when the problem is you have to create a small layer of the powder or cut the battery residual. So this is an example of the workflow. You have here a block mass from initial scan observations, and this is a 3D X-ray reconstruction. You can see low density materials, high density materials. And the idea here is we want to understand what is happening there, what kind of materials you have. Now we can use, again, the standard reconstruction, but then you lose a lot of the information because of the noise added to the reconstruction. And what we have done at ZEISS is use deep learning, we call it Deep Recon Pro, to get rid of the noise, understand what is noise, and get the data back. So you can now do segmentation, use segmentation algorithms, or visually identify different types of materials. And in fact, you can segment those type of materials and create a characterization in terms of the type of materials that you have inside with different types of colors. And you can see an inference here of the type of materials that you get inside of this black mass. This is very useful when you finish the scan. You can create a characterization in terms of percentages and different types of materials that you see inside, and then let you decide how to use this in a recycle mode. Here is an example of when you have original data model and then the subsequent secondary data using the same model, how you can use it. This just to highlight that there is a caveat in the deep learning. You need to at least collect a high quality image of one sample, at least, to do the training. Once you have that, then you can use the training model with the subsequent types of data or samples that are the similar type of material. So here is a little bit of a summary of this method that you can use now for analyzing the black mass characterization that you want to use for recycling the materials. And you can use X-ray microscopy to characterize that in a non-destructive way and try to get information of what is inside of this big black mass block before you try to reuse it. And if you want to use the now electron microscopy, it would be a nice complement to use after that for sure. Let me then try to do a summary here so I can give you enough time for questions. I have talked today about the power of X-ray vision to see inside of batteries without destroying them in a non-destructive way. And we have introduced, maybe for some of you, a new technology, which is X-ray microscopy. X-ray CT is very well known, but X-ray microscopy not so much. We can get higher resolution into small parts of the battery, still without cutting the battery, to see deep into the materials. And that's the main advantage of what I have introduced today with X-ray microscopy. Of course, you can see the battery in a full assemble mode, and it enables you to inspect with either X-ray microscopy or X-ray CT, especially if you go to larger battery formats, prismatic batteries, or even battery modules or battery packs. You can see inside of batteries to see the different components and do a quality inspection after several cycles of charging and discharging to see if the electrodes are aligned, or is there are any overhangs, or there are degradation. And you can go also back to X-ray microscopy to analyze now the residual materials that you want to recycle. You want to reuse them to build new batteries. But before that, you need to understand really what is inside of, what are the components that are left after you have used a battery. And X-ray microscopy can be used for that. One additional thing that is really worth mentioning is that we have empowered the X-ray vision not only with the ability to see inside, but also with the use of artificial intelligence, in particular deep learning algorithms that are being trained to identify what is noise in the reconstruction or artifacts, get rid of them, so you can have recover the data and really analyze purely data that doesn't have noise or minimal noise. And with this, I think I'm going to stop here to give you time for questions. All right, let me see. So I have here some questions. I have one question for Vin. Does X-ray could do evaluation on battery cell wattability? Vin, are you online? Can you elaborate your question?
Yeah. Can you hear me?
Yep.
Hi. Oh, thank you for hosting this information for sharing the X-ray technologies. So my question is, I'm trying to do some evaluation of battery cell before the formations. After you fill the cells, right? The electrolyte should be soaked into those stacks.
Yeah.
Want to see if this X-ray can detect how the cell wetted, or how the soak goes on, if it's like a wet distributions, or if it's the cell is half wetted or full wetted, or too dry, or is it possible to do from X-ray?
So the water would be low density, that is gonna be difficult to differentiate, but the way you can do this is that you see effects on when you do before and after, you see some changes in the battery. So if you can identify some changes that you can attribute to the water, then yes, potentially you can use it. But to identify water in itself, I think it's going to be a little bit challenging.
Okay, I understand. Thank you.
Yeah, you're welcome. We have another question from Liam, and please feel free to keep putting the questions in the chat, so I can answer them. Or you can open your mic after I finish these two or three that we still have here. Okay, we have one from Liam that says, can this tech be used in line as opposed to a lab, say for a high volume manufacturing environment or for processing supply cells? The answer is yes. And we have some technologies coming up for that to do very high throughput verifications of batteries. The only catch is that then you have to be very targeted or very focused on a particular task. And in this case, let me just put one example. You want to detect overhangs, and you could do this with a very fast throughput 2D system, in line or almost at line, like very close to the line. You could do this. The other possibility is that you want to inspect 3D the batteries, and you just want to inspect for particles inclusions or for voids. I mean, you can start adding to the algorithm what you want to detect. That is also doable, but again, because you're going too fast in terms of the scanning, then you're sacrificing details on the 3D reconstruction that doesn't allow you to identify, I don't know, any other analysis of particles in the electrode, but you're just targeting high density materials that are inclusions, and that's doable. If you want to identify also voids, that's also potentially doable. So I could expand more on that, but I think we can follow up offline if you contact me later. We have one from William. What are the resolutions of your XRM and your CT scans? Are they similar? Yeah, that's an important question. So when we are talking about X-ray microscopy, the best resolutions, and you saw the difference between X-ray, XRM or X-ray microscopy and CT. The XRM can see down to particle level distribution of the anode. And those resolutions are in the order of 1 micrometer or below, down all the way down to 700 or 500 nanometers. That's doable. With X-ray CT, you cannot go down to that level. The resolutions start in the most optimistic would be 2 microns, but I would say 5 microns is more realistic and above. So when you are using X-ray CT or computer tomography scans, it's mostly for checking the electrodes and high density materials, and sometimes when you have the battery packs, then you check the electronics and the things that are around the battery itself. So that's why when I started the conversation, I said we go from battery materials to battery packs, and I differentiated the two technologies where the focus are, and that's translated into resolution.
You know, Herminso, I have a follow-up question, and it's not totally clear to me. I just want to make sure that these are different separate machines, right? You can't just buy. You're not buying one machine that does.
Correct. No, it's you're right. You're right. It's and the reason being is because when you use X-ray microscopy, then what you're targeting it's high resolution. We add to the system some additional optics that convert the X-rays into light, and they go through a set of lenses that magnifies the image, so you can get some extra resolution from that. The other thing is you need to keep the kV, which is the measure of energy acceleration voltage, down to maybe 160 kV or below. If you go up from that, then you start losing resolution, but then you gain penetration. You can get through thicker batteries, like a prismatic battery or a battery module, and that's where you would need the CT.
That's why you need density, you said, or I'm sorry.
More powerful CT systems that give higher kVs that accelerate the X-rays at a higher energy penetration power.
That's density. Okay, thank you.
You're welcome. Okay, well, let's go with Barry's question. Once you have the noise, the data set, do you have tools that can analyze the entire cell, all the 2D slices for behavior-induced or manufacturing-induced anomalies, or does the clean data need to be exported elsewhere? Yeah, so the noise data or the noise algorithm that we created is working in the projections before it going into the 3D data reconstruction. So what we specialize is in producing the best images that you can get for your data, so you can analyze that afterward. Once you have the data, you can import the data in several types of analysis software that are out there. We tend to use Dragonfly. We also have an internal software, which is ZEISS Inspect. And you can now, in that software, you can use other types of tools to do the analysis that you want to do, including some additional AI tools to facilitate your work in terms of segmentation or create the analysis you're wanting. Does that answer your question? I suppose yes. Now I'm gonna go with Komar question. Does XRM work on lead acid battery anode cathode like your black mass detection? Yes. So the technology is independent of the type of battery. Of course, you might have some challenges depending on the density of the anodes, but the technology is the same. It applies for any kind of battery. So again, low density materials are gonna pose more challenge, but it's doable. At least we can explore. And testing one is the best. It's gonna give you the answer. I'm gonna go with the question from Vin. One more question: does there any application for do measurement on the scanning images like length, width, and area, etc.? Yes, all of that is possible to do, especially with the analysis software from ZEISS. ZEISS Inspect. It has all the metrology tools that can be used to do measurements. And one very typical, just to give you one example, is to measure the overhangs. So in this image that is on the screen, you measure the distance between these electrodes and the end of these overhangs. And if they have some difference between them, then you can flag them as out of tolerance or so. I don't see any more questions in the chat, but if any,
Can I ask one more?
yes, you can ask more. If you just open your mic and go ahead.
Lithium doesn't have a very high X-ray scattering cross-section.
Correct. Yes.
So is that something that is, I mean, can you actually see lithium?
It's very hard to detect. We do have an additional system that is called the Ultra XRM, and we've done some experiments, but we see the trace of lithium, but not the lithium per se. So we can see some of what happens afterwards, but yeah, you need an electron microscope for that.
Okay, thank you.
You're welcome.
Just to make sure that XRD can detect lithium, is that correct?
No, you will have to use an electron microscope. I mean, we could try to do some experiments with an Ultra XRM that we have that is very low energy. It uses 7 to 9 kV, but I think it's still challenging.
Thank you.
You're welcome. Okay, if that's all, I do appreciate you for coming, and I hope you enjoy the rest of your day. Thank you so much.
Thank you very much.
Ciao for now.
Ciao.